All right, so this last lesson is going over how to solve proportions or ratios. Fractions and ratios are essentially the same thing. We use ratios when we're, like, if you ever go into statistics, you're trying to understand, like, the demographics of a population or something. So maybe you have a 50 ratio of people who, I don't know, people who skateboard and people who don't skateboard. I don't know, right? Let's say half of the world skateboards. Okay, so for every 50 people who skateboard, there are 50 people who do not skateboard, right? So this is the skateboarders, and these are the non-skateboarders. Okay, and you can simplify this, right? A ratio means that you can simplify it. 50 over 50 is just 1, right? Or 1 over 1. So that means, like, for every skateboarder you find, you're also going to find a non-skateboarder, right? In this made-up world. Was the first thing that popped in my head. Right, so you can do this for any fraction, right? This is simplifying. We've found equivalent fractions before. Okay, so 6 over 16th, same as 3 over 8, right? Maybe that's probably more realistic. For every 3 skateboarders, there are 8 non-skateboarders. It's probably not even that high. Okay, so hopefully I don't have to go over how to simplify that again, right? But we're just finding these ratios, and they represent a population. They represent a proportion of the population, and what they represent, in this case, it was skateboarders to non-skateboarders. Okay, and so if it helps, you can think of it like a visual. So maybe if you think of, like, 2/4, right, is the same as 1/2. If you look at it visually, okay, let's say you have a piece of pie. Ooh, sorry, one got. Okay, if it was cut into 4 pieces, like these pies are the same one. If it was cut into 4 pieces, I ate 2 pieces. Out of the 4, I still ate half of the pie, right? Whereas if I cut into 2 pieces, I still ate half, right? You can see how that's the same. Fractions are just how much you break apart something. And we're showing that these 2 fractions are equal to each other. They are proportionate. They are ratios with each other. So even though I broke the pie up into more pieces that time, I still ate the same amount. I still ate half of the pie, no matter whether I cut it into 4 pieces, 2 pieces. Maybe I did it into 8, right? If I did it in 8 pieces, what would that be? Then that would mean I had eaten 4 out of the 8 slices, right? That's what proportions are telling you. We use this a lot for percent, and just also, like, using it for scale. When you're, like, an architect and you're building models, you're drawing things to scale, like on a blueprint, that kind of thing. You're going to say, like, oh, on a map, 1 inch is equal to 25 miles, because I'm not going to draw a real life size map, right? That would be not useful. If we were trying to, like, read a map that was the same size as the world, then what's the point of having the map, right? So we make a small to-scale map so that we can estimate where we are. Okay, so solving proportions. Right, so let's say you have, it's a really simple, if you have 2 fractions, and this is, like, when we're trying to figure out, like, maybe we have a variable somewhere in there, right? We're trying to figure it out. You can use this method to solve it. Okay, so if A over B is equal to C over D, then if you use this rule, A times D, so this is what cross multiply, equals B times C. Okay, so some people call it like a butterfly or whatever. I've never heard that, but students have told me about it. I just call it cross multiplying, right? Cross multiplying. And really it just comes from like, we'll do that example again. So maybe we have, it's the same fraction right here, but we're going to actually solve for our missing number x, right? What does that x represent if these two fractions are supposed to be proportionate to each other, right? If I think about how I'd want to get x, solve for x, right? I want to solve for, what does x equal? Okay, so first of all, x is at the bottom of a fraction. I don't want to know what, you know, a fraction of x is equal to. I want to know what x equals. So I need to figure out how to get my x on the top. Okay, so one way I can do that is by multiplying by the reciprocal. That way I'll cancel out, right? But then if I'm going to do it to one side, I do it to the other, and that way I'll get x on the top here. Okay, so I'll get 3x over 8 equals 6. All right, I got rid of the x on this side and I moved it to this side. So this is just like solving fractions with multiplication and division. Okay, so you know how to do this. We've done it before, so I'm getting rid of that x on the bottom. Instead of dividing by x, I multiplied by x. And I transform. If I do it on one side, I have to do it on the other. Okay, so now I'm getting closer to solving the x. X is now on the top, which is what I want, right? I want to figure out what x equals, not 1 over x equals. Okay, and then I need to get rid of this 8. So again, since I'm dividing by 8, I can multiply by 8. And I have to do it on both sides, because I'll get 1 here. So I'm left with 3x over 6 times 8. And if we look, that's just me cross multiplying, right? 3 over 8 equals 6 over x. If I just cross multiplied, 3 times x is 3x, 8 times 6, or 6 times 8, either way you want to write it. Right, you can see I basically cross multiplied. So it's just, instead of having to like think through all these steps like here, you can just remember this cross multiply rule and it'll get you to this step much faster. Okay, and then I can solve for x. Okay, and then I divide both sides by 3. X equals 16. Right, which we knew it should equal 16 because it's that same fraction I used up here. Okay, so I just proved why cross multiplying works. So now that you know that, you can, whenever you see any kind of equation that it looks like two fractions, a proportion when two fractions equal to each other, you can just, instead of having to do all those steps, just do the simple one, cross multiply. Why did I pick those numbers? 27 times 5. Okay, I want to solve for x, I have to get rid of the 10. So 135 divided by 10 is 13.5. Okay, so I solve for x. So bottom of that fraction is 13.5. You can always check this if you wanted to check it. You could plug in 5 divided by 13.5 in a calculator. And you could do 10 divided by, oh, why do I always leave my phone in the other room when I do this? I can't check it for you. But if you plug each of these into a calculator separately, 5 divided by 13.5, see what you get. 10 divided by 27, see what you get. It should be, you know, whatever you get in the calculator, it should be exactly the same. Okay? Like, if you plug 3 over 8 into a calculator, you'll get 0.375. right? 3 over 8. If you plug in 6 over 16 into a calculator, you will also get 0.375. Right, so just to further show you that these are in fact equivalent. Okay, and that's just me from me substituting 13.5, oops, into x. Okay, let's do another one. So you might get a little bit of a tricky one. Okay, where you see there's an expression now on the bottom. Don't get too thrown off, but, so I'm going to cross multiply still. 2 times 9 is 18. The only thing you have to remember is take this as a whole number. Okay, it's x minus 2 as a whole, as like a unit. That means, if it helps, I would just put parentheses in there, because then what it's going to do is going to make you remember to distribute. So it's 4 times the whole number of x minus 2 as a unit. Right, 4 times parentheses x minus 2, and then that way you'll remember to distribute, because if you don't put those parentheses, you're just going to say 4 times x minus 2, and you're going to forget to distribute to the 2, and you're going to get a completely different answer. So you have to, if you see like an expression on the top or bottom, put it in parentheses immediately so you remember to distribute. Oops. Ugh. Right now I'm just solving for x, so I'm going to get rid of the 8 on that side. I get 26. Why do I keep picking numbers that give me fractions? Sorry. Right, 6.5. And I'm in your homework, I didn't answer the fractions. I don't know, I'm just kind of putting numbers. And then I just keep accidentally making them fractions. All right, so, like if you want to think of real life examples, so let's say you're looking at a map, and the map says that you've got a map, the legend says 1 inch equals 25 miles, okay, on the map. So then I want to know, what does 3 inches, how many miles is that, right? So if you think of it as a proportion, 1 over 25, right? 1 inch per 25 miles. So 3 inches per what miles, right? We're going to label this as our x, try and figure out what that is. Because they should be equivalent, they're proportion. The map is not going to, if our maps change like that, where 1 inch is 25 and 3 inches is, it's not to scale, then it's kind of a useless map if the distances don't correspond with real life, right? So they're going to be proportionate. So let's solve for this. Cross multiply. 1 times x is just x. 3 times 25 equals 75. Right, so if we have 1 inch is 25 miles, that means 3 inches should be 75 miles. Okay, so maybe you work at a grocery store. There are people who do like marketing and things like that, and they'll find that 9 people will buy regular milk, or whole milk, and then like 5 people will buy 2% milk, right? So they find most people, for every 9 people that buy regular milk, 5 people will buy 2% milk. Okay. So, there are people that's their job, it's statisticians, that's such a hard word, who like study like how products are bought off of shelves so that they can optimize how much you're going to buy, so that you don't waste, especially when it comes to milk, you don't want to be buying too much and then it goes bad before all your stock runs out. So they're always like analyzing what gets bought in the grocery store and whatever store, retail store, so they know what to put in inventory, right? So let's say you have, why did I pick such a bad number? We'll do 72. Right, so let's say you have, you're gonna order like 72 gallons or whatever of whole milk. Right, how much 2% milk should you buy to stock up? Okay, so again, this is a proportion. We know that 9 people, you can, right, 9 will buy whole for every 5 that buy 2%, right? So that means 72. So if it helps, just remember you're doing whole to 2%. Okay, so 72 whole, and I'm trying to find out how much 2% should I put on the shelves, should I order for my next batch to kind of keep in proportion so I'm not like buying too much or too little, right? And then now it's just a proportion problem. 9 times x equals, oh, I did it to myself. 72 times 5. You know what I'm gonna do? 72 divided by 9 is 8, right? Divided by 9. 9. So then I'll get 8 times 5, so 40. So I should be putting in 40 gallons of 2% milk. Right? That's how much I should be stocking in my store if I plan to buy that much gallons of whole milk. Okay? Yeah, so those are just some examples of proportions. Oh, percent. If you want to do a percent problem, right? So let's say we know that 60% of adults, I'm just making all of this up, have a driver's license. Okay, we're just say that's what the data says. The data says this many people have a driver's license, 60%. There are 500 students at South Seattle College. Again, these are all lies. So there are 500 students at South Seattle College. How many drive or have a driver's license? Right. And it's like, so this is kind of an estimation. People do things like this based off of like real life data, and they were trying to find out, okay, the demographics of our students, based on real life data, how much of them drive, so that we can figure out how much bus support we need to be giving to our students. Like, right, how many Orca cards do we supply for students? How many parking spots do we need to make sure are available for students? Right, so this is kind of like going into just knowing basic data and statistics so that schools can optimize their campus to serve their population better, right? Okay, so, and I made these numbers up, so don't take it seriously, but right, so we're trying to estimate based on what we know from studies of how many people drive, how many of our students drive, so we can know how many parking spaces should we allot to students in our parking lot. Okay, right, so percentage is always out of 100, so we know that 60% means 60 out of 100. Okay, if you have 100%, that means all 500 students would drive, right? But we want to figure out what percentage of 500 students drive. So we have the total number of students. We don't know how many of them drive, but we do know it should be equal to like the 60 over 100. And again, I picked numbers. That's going to be hard to 100 times x equals 60 times 500. I'm going to do the division first, because then I can just do that. So 60 times 5, 5 times 6 is 30, so it should be 300. So 300, so we're going to estimate out of all of the students, about 300 of them probably drive. Okay? And so, you know, maybe they're going to build their parking lot based off of that or whatever. They probably put in other data too, like how many actually own cars, right? There's more data on people who own cars versus have a driver's license, right? So they can really figure out the optimal way to design their campus, right? But that's percentage. And yeah, so these are all proportions. We use it for lots of different things for scale. It's really useful to know proportions, and so much of data and statistics, like basic data and statistics with stocking your store, designing a campus, urban planning, everything, proportions are such a huge part, percentages. Right? All right, so we'll stop there. That is all the lessons for this week. There's only 4, but fractions I know are tough, so like go over it as much as you need to, and please